All right, so next we have Tevfik Bultan from UCSB. He's going to talk about modular software verification.
So this talk is about this work we have been doing for modular verification, as John said. And we use these interface grammars. Basically, it's an interface specification language that we developed to achieve modular verification. So the talk is based on these papers. I'm not showing these to advertise our papers. Well, actually, partly I'm doing it to advertise our papers, but actually this is mainly by Graham Hughes, my PhD student. So the work is based on his dissertation. As you see, he's the first author on all these papers. So hopefully he's going to finish his dissertation this summer. So I'll talk about what interface grammars are and give a case study, verification case study. And then I'll talk about how we applied this to verification of web services, client and server-side verification. And then I'll show another case study about that. So our motivating problem is model checking, software model checking. And model checking is an automated software verification technique, right? The basic idea is exhaustive exploration of the state space of the program. So try to check all possible behaviors of the program and look for violations like assertion violations or deadline. And there have been some model checkers developed for programming languages like C and Java, and Verisoft, Java Pathfinder, Slam, Blast, CBMC. So there are some model checkers out there. In our studies, we used Java Pathfinder, and we focused on Java programs. But the techniques we developed could be adapted to other software model checkers too. So what is the problem with model checking? Well, first of all, it's a very ambitious thing to do. Checking all possible behaviors of a program is, well, impossible based on some undecidability results. But even if you bound the state space to a finite state space, it's decidable, but it's very hard. Because state space includes everything. All the threads, variables, control stack, heap. But so there are these tools out there that try to do this, right? Of course, they have a lot of techniques that try to improve this state space exploration. And so therefore, it's not just a naive state space exploration. But still, state space explosion is a big problem. So if number of variables or number of threads increases, performance of model checkers get worse and worse, right? Now, environment generation is another problem. So you don't have access to all the components of the software you are trying to check probably, okay? And the simple thing is there may be a user providing input. And so you have to model the user's behavior. You have to provide some input to the program, right? So that's the part of the environment. Or this is a distributed program, and you're trying to check one component. It's interacting through the network with some other component. Well, you have to somehow model this other program that you're interacting with. So that's the environment. Again, you have to somehow model the environment of the part that you're checking. So these two problems are actually related. So to fight state space explosion, you want to do as modular verification as possible. You want to divide the program to parts that the model checker can handle efficiently. Well, if you want to do that, then you have to provide an environment for those parts. And therefore, you need environment generation. So these things are related. And so one of the key techniques people used over and over again is modular verification, right? So modularity is the key to scalability. If you can chop up a small piece of software and just somehow focus on that and try to verify that part, then hopefully you can do better rather than trying to verify the whole system together. So another thing is actually modularity is a key concept in software design, right? So ideally, you would like to exploit the modularity in the program with your verification tool. So this is not. I think this is still a direction that should be explored, and I don't think we explored it as much. So our this work was motivated with this somehow, use right interfaces to show the modularity in your software, and therefore use those to achieve modular verification. So how to do modular verification? Well, divide the software to a set of modules, check each module in isolation. So that's the basic idea, right? It's a divide and conquer approach. Now, how do you isolate a module? So you want to write stubs for representing other modules. Like you want to provide an environment for the module that you are focusing on. So how do you write those stubs for the other modules that you are not going to focus on? Write interfaces, and from those interfaces, try to generate these environment for a module. So try to generate the environment of the module you are checking using the interfaces of the other modules. Okay, so that's the basic idea. So from interfaces, generate the stubs. So what is our approach to interface grammars that we are working on? So user basically, it's a semi-automated approach. So we are not trying to discover interfaces automatically. So we are saying, OK, here is a way of writing interfaces. Use these interface grammars to specify the interface. And we have an interface compiler that's going to take this interface specification, and it's going to generate some Java code, which actually is a stub that represents this interface. There is going to be some non-determinism in this stub, actually. So that's, and so it's going to allow more behaviors than the module you are replacing. And this automatically, using this automatically generated stub, verify the component that you want to focus on. So again, the scenario is I have two components maybe, and I want to check component A, okay? So write an interface specification for that component B that you don't want to check. Oops. So now we take the interface grammar that you wrote, we feed it to our interface compiler, which is going to generate a stub for that component, okay? Then we'll use the model checker to check this component A with the stub of component B together. So the state space, hopefully the state space of this thing is smaller than the state space of the full system with the full component B, right? So that's the motivation. Now, so that's the basic idea. I'll give you some examples. So what's an interface grammar? So, and the way to think about it is you can think of this as YAC for writing interfaces. So you basically write these context-free production rules describing your interface, and then we compile it to something that basically behaves like that module that you wrote the interface for. So I have a small example here, and we do it at the basically method call level, all right? So it's like at the API level. So this is a very simple interface grammar for transactions, and all it does is you want to first get the begin call, and then each begin call is going to be followed by either a commit or rollback. And that's all I want to see, all right? First a begin, then possibly a commit or rollback, then another begin and a commit. And this would be the grammar for writing that, right? It's a very simple specification. Now, method calls become the terminal symbols of the interface grammar. So we are recognizing sequences of method calls, all right? So here is, if you get a call sequence like begin, rollback, begin, commit, this grammar should recognize it. And how do you check that? Well, you can show that there is a derivation. You start with the start symbol, goes to non-terminal base. That goes to, based on that production, goes to begin, tail, base. Begin is the terminal, it's the method call. And then that tail goes to rollback. Base goes to begin, tail, base again. And tail goes to commit. Base goes to epsilon. And we have a parse for the call sequence. So this grammar becomes the specification of the interface. Now, you can say, well, actually, this idea, people have been doing this for a while. You use state machines, actually, to specify interfaces like this. So the interface I showed you can be also specified using a simple state machine. And this idea has been used a lot in verification, right? So use a state machine, and there is a state machine for that interface. But with grammars, you can do more. So if you had nested transactions, where basically you can nest within a transaction another transaction, then you can't do it using state machines. So, but you can still do it with grammar. So this would be the grammar for the nested transactions. And it allows basically you to do begin and then another begin and then rollback maybe and then commit, so, or rollback. So you can nest the transactions, right? And so now, OK, so this is fine. You can do some stuff using just these context-free rules. But typically, if you want to generate stubs for some component, things are not that simple. You'll need some, these method calls are going to have some arguments. They are going to have some return values. So how am I going to specify that? This is kind of similar in YAC, right? You don't only specify a context-free grammar. You also specify some extra semantic actions which actually do stuff when they, the productions are used. So we also allow semantic actions and semantic predicates. So assume that for nested transactions, I want to add a setrollbackonly method. And when you call that, all the pending transactions have to be rollback instead of commit, OK? So if I call setrollbackonly, after that, I only want to see rollback. I don't want to see a commit until all the nested transactions are completed, OK? So how do you do that using the interface grammar, where we add some semantic predicates and semantic actions. So here, what we added is a flag R, which is basically indicating if the rollback-only status is set or not. And L is the level of nesting, OK? So I added two variables. Now, this is outside of the context-free rules, right? It's these variables that I added. And here with semantic predicates and semantic actions, I'm actually checking or updating the status of these variables. So for example, this is a semantic predicate. It says here, tail cannot go to commit if R is false, OK? Oh, sorry. Tail can go to commit only if R is false, OK? Otherwise, you can't go to commit. So, and then here, for example, I have some semantic actions which actually set, here R is set to false, here it's set to, level is set to 0. And when I begin a transaction, I increase the nested level by 1. And if I complete a transaction after the tail, I decrease the nesting level by 1. And if the nested level is 0, then I reset the rollback status to false. If I see the set rollback only call, I set the rollback status to true. After that, I will only allow rollback. OK? So the moral of the story is we can do more with grammars if we add these semantic actions. And we can actually even write constraints about the arguments of the method calls. And we can say, the argument of commit has to be this. And I can put a semantic predicate there expressing a constraint. Or I can construct a return value and return some result specified here. So our language basically supports semantic actions and predicates, and these are in our language are actually is Java code. So you can insert Java code here for semantic predicates and actions, and you can do a lot of stuff. So what do we do with the interface grammar? We have an interface compiler, so that's the tool actually we built, right? So it takes the interface grammar, takes this language, and generates a stub, basically that corresponds to a parser for that grammar. So and that is going to be the stub for that component. So just to show the, so visually this is what happens, OK? So I have a program. This is component A, let's say. And then there is a part of this program that I don't want to analyze, OK? That's maybe outside the scope of my model checker. My model checker is not able to handle certain things there. Or I just want to do modular verification. And so what I'm going to do is I'm going to write an interface grammar for that component. My interface compiler is going to generate a stub. So this thing is the stub. And now program is going to call the stub. And that thing is going to behave according to the interface grammar and return values. So this stub is actually a parser. So it parses the incoming method calls based on the interface grammar. OK? So, and semantic predicates and semantic actions also construct return values and stuff. OK. So we did this, and so other than modularity, I mean, another motivation was, for example, we were using JPF, and JPF, for example, cannot handle native code, right? So you have to write by hand stubs. So we wanted to have a more systematic way of doing this. And so can we kind of like rather than writing some Java code every time we want to stub out something, is there a more systematic way of, writing these stubs? So if you can kind of develop an interface language that can be translated to stubs, that will be helpful. So we chose these grammars, but the same idea can be used with different languages, right? So we did a case study using EJB persistence API. So this was basically, okay, can we write meaningful interfaces using this language? So we wanted to try that. So, so we wrote a interface grammar for EJB's persistence API, right? And and then we wanted to show that, okay, we can do some model checking with this. And the case study we did actually is we used the Hibernate test cases that are developed to show that your EJB client, basically checks the Hibernate implementation by providing some clients, okay? So, and then it, for example, has some error cases in it. It's supposed to raise an exception, and that showing that your implementation of the EJB API is actually correct, okay? So we use those clients to show that we can actually stub out the complete EJB persistence API implementation and do the client-side verification. So what we are doing is actually checking the client, okay? So if you want to use JPF to check these clients, it doesn't work because JPF is not going to be able to handle EJB. So you have to write stubs. So we write the interface compiler, stubs are generated automatically. So now there is manual part in this, so you have to write the interface grammar. So, and then we didn't do any kind of empirical evaluation of how difficult that is, but it took Graham a couple of hours to write it. I mean, part of our motivation for using interface grammars is people are familiar with this type of stuff. People use YAC, so they should be able to write these context-free rules and understand what's going on. Of course, you still have to understand the interface. So he had to read the EJB persistence API and understand what the constraints are. But after you learn that, you should be able to write the interface grammar. So then we did verification with some of these clients that were with the distribution. These are simple, very simple pieces of code, okay? So the verification time changes from 2 seconds to, whatever, around 2 seconds, right? And these were very simple examples, so we tried to parameterize them. So they do like one operation and check if the return value is correct, right, based on the API specification. So what we did is kind of put these operations in a loop so that you do multiple calls, okay? We also created multiple objects and, so we made these simple examples parameterized. And then we tried to check, how does the verification or falsification performance change with respect to when you increase the parameters, you create more objects or you loop more. And falsification performance doesn't change. So, and this is not surprising for model checkers, right? So if there is a bug, you find the bug, you do a depth-first search, and maybe if you iterate more, still, if you are able to find the shortest path, not necessarily the shortest path, but a path to the bug, increasing your state space doesn't necessarily change your time to reach to the bug, okay, if you are doing explicit state enumeration. And so in these examples, when we increase the parameters, if there is an error in the client, you still reach it pretty efficiently, okay, in a couple of seconds. Now, however, after you remove that error, okay, so now there is no error. Now, to verify the client, you have to explore the full state space. And now, verification time increases with the state space size. And here, so the verification time increases, I think, linearly with the number of objects and quadratically with the number of iterations, which is actually each iteration, the number of operations increases quadratically with the number of operations you do. So so verification time increases linearly with the number of operations you have, okay? So the point is, okay, so it goes to a couple of minutes, even for these simple examples, if you add loops, basically. That's the moral of the story here. You know, we have a loop, we iterate 5 times. But the point is, we couldn't do this with JPF before, right? So, I mean, there was no way you could analyze the full EJB. Now, at least I have a way of checking the client's EJB clients. Okay. And the falsification time is pretty efficient, which is what I said. So now there are some, so this, for this case, actually, our initial setup was, we will have an interface for a component that's actually called by some, the program, and we will just generate the stub for that component, and we restricted the case that there is no callback from the component to the caller, right? So, so that was our first iteration. Then, of course, you may want to generalize this. You want to say, okay, I want to handle callback. So I call this component. I'm going to generate a stub here, but the component calls back. So that is possible to do. So we extended to that. You can do that. Another thing you may want to do, I don't only want to do client-side verification. Okay, so I'm calling a component, and I'm going to check the client, so I'm generating a stub for that component. Maybe I'm going to do a server-side verification where I generate a driver. So you may want to, using the same interface, you may want to generate 2 different things for different directions, okay? So you do both client-side and server-side verification, okay? And so we also did this for web services, and I'll talk about that a little bit. How many minutes do I have?
Like 15 minutes.
15 minutes more? Okay, good. So I can talk about that part too. So, for the web services, what we did is based on this idea. So basically, there's a web service provided, right? There is a WSDL interface for this web service, let's say. And I want to generate, basically, we write this interface for the web service using an interface grammar. Then our interface compiler generates a stub for that web service, which I can use to check my client, right, which is calling the web service, to make sure that it's passing, appropriate arguments or the operations are called in the right order. Or I could generate a driver to check the implementation of the service, make sure that my understanding of the interface is correct with respect to the implementations that's out there, because maybe I misunderstood what I'm supposed to do. How am I supposed to interact with the service, right? Another part of this is actually that I won't get into. You can throw in all the data manipulation, all the issues about the arguments and data structures to semantic actions and predicates, okay? So the control flow, the context-free syntax doesn't show anything about the data structure, let's say. So that's one way of doing it, okay? Do all the data checking or data creation in semantic actions and predicates. Another way of doing it is, can you actually use these recursive rules to somehow show the data, check the structure of the data, or construct the data? And this can be done, so we have a paper on that too, where we use grammar productions to actually both validate the structure of data and also construct data. And so this is basically can be done with recursive data structures. Not all of them, but a lot of recursive data structures can be done that way. So, so for the web services, so this is the scenario I was describing. We have a web service client which is making SOAP requests to a web service which has a WSDL interface, okay? And it's getting SOAP response. So I want to check the client and the server, and I want to make sure that they behave according to the interface specification. So we have 2 steps. We have it's again semi-automated. So from WSDL, actually, we take the WSDL specification and generate some portion of the interface grammar. Okay. So that portion is basically going to check for example, your types of your arguments, the XML data that you send is correct with respect to the WSDL specification. So it's going to do kind of like XML type checking, okay? So that's one part. But the WSDL itself doesn't contain any control flow constraints. So you may have constraints like you have to call operation 1 before you call operation 2. And that's not in the WSDL specification. So that you have to insert manually in your interface grammar specification. So basically, we'll automatically generate some core interface grammar for you from the WSDL. And then you have to add more stuff if you have more constraints, okay? And then we'll generate the client and the stub, client and the server driver, the driver for the server and the stub for the client verification automatically. So again, this is the overview now of what's going on. So you take the WSDL specification, we generate the server interface grammar or the client-side interface grammar. You add some control flow constraints, and the interface compiler is going to convert that to either a stub for client-side checking. So this kind of simulates the server's behavior, okay? And or a driver for server-side verification. Now this is, so you definitely have to do something like this by hand if you are writing a client for some web service, right? Because you don't want to keep connecting to by sending SOAP requests and testing this thing just by connecting to this real service. So it would be, first probably you would do something, write a stub here to check that things are working fine before you connect to the real service. So we are doing that semi-automatically, basically. So we tested this approach using Amazon's e-commerce web service. So Amazon has a bunch of web services, so we checked this e-commerce one, which basically lists about 40 operations that Amazon provides to search their product database, okay? And we focused on several of those operations, like item search, cart create, cart add, cart modify, cart get, cart clear, okay? So there are constraints on how you can call these operations, okay? So that will be, those constraints will form the interface. So, so for example, you should not try to insert an item to a shopping cart before creating a shopping cart, things like that. So there are some constraints, right? So, so we did basically, we again wrote an interface grammar, part of it automatically generated from WSDL specification, and then from this interface grammar, we generated a stub for client-side verification. So for client verification, what we did is Amazon has a demonstration client showing that, okay, so if you wanted to implement a client for our web service, here's how you would write it. Now, this client doesn't do any checking on the requests that are sent to Amazon, okay? So it's just for demonstration. So it has, so if you want to say, so if you implement this client, it's possible that you will send weird requests to Amazon and you are going to get some error message saying that, whatever, some XML report saying this is not, doesn't make sense, something is null or whatever. So maybe a better thing to do at client side, make sure that you check what you are sending is reasonable, and if user requests something weird, like deleting a cart without creating one, you give an error message without sending that to Amazon, okay? So then it would be a reasonable thing to check if your client, whenever it connects to Amazon, does it send some reasonable request? So that's basically what we checked. And for this demonstration client, there are lots of errors because it doesn't check anything. So you easily find errors in it. But it still takes about 10 seconds to 60 seconds, depending on the type of error you are looking for. So we both looked at like data errors, data, nonsensical data sent, or control flow errors, okay? So then server verification was basically, I'm running out of time, I think, but so server-side verification was checking the Amazon service implementation that's out there, right? With respect to our interface grammar, basically with respect to our understanding of the interface, okay? And to do that, basically now, rather than parsing the method calls or the SOAP requests, what we are doing is actually generating sequences of calls based on the grammar, okay? So now we are actually doing sentence generation rather than parsing, okay? So we did 2 types of sentence generation. One, completely random, so randomly pick productions and generate call sequences. The other one, have a coverage criteria and try to generate sentences for that coverage. And the coverage criteria we picked was production coverage. So I have a grammar. I want to make sure that the sentences I generate at least use each production at least once, okay? So, so for this directed sentence generation, we use something called Purdam's algorithm by Purdam. And it generates 5 call sequences. It covers all the productions we had. Average derivation length, basically average call sequence is 24 operations. So it basically makes 24 SOAP requests to Amazon, and 5 of those. Oh, OK, sorry. That was the derivation length. That's the derivation length. Actual average number of calls to SOAP is about 4 calls per sentence, OK? And so if you generate these 5 sentences and make these calls to Amazon, it takes about 20 seconds to check, see what happened. We also did randomly. So randomly, you are generating sentences randomly. So we generated up to 100 sentences, OK? So, and then, of course, you generate more call sequences, your cost increases pretty much linearly with, how many times you execute this thing. And for 100 call sequences, we get about 300 seconds to check. These are seconds. And in terms of production coverage, if you want to look at this production coverage as a criteria, after about, I think, 40 or so sentences, even random generation gets full production coverage. With the other algorithm, you just need to generate 5 sentences because it tries to get production coverage. So we found 2 errors. Now, errors, this doesn't mean that the Amazon Web Service implementation has a bug. It means that there's a mismatch between our understanding of what it's supposed to do and the implementation. So our understanding was based on the specification to be read. So this is what you want to find, right? I mean, it means if you are writing a client, if you misunderstood it, you will have a bug. So it doesn't matter. I mean, so you need to understand exactly what they are doing. So this is a way of resolving that, right? So to conclude, I think, so I really believe that modular verification is the key if you want to do automated verification. And yeah.
Which of the 2 phases?
Oh, so what were the bugs? So the bugs, one was basically, I think, a container that has a container in it. Okay, so there's a list within a list. And what happens if the list within a list is empty? Is the other, the containing list empty or not? So the outside list, does it contain one element which is a list, or is it an empty list? And so there was a misunderstanding on what they had implemented and what we thought we would get, right? So it's a very corner case. So that was one of them. And the other one was actually, I think, related to control, that you can't keep adding, you can't have multiple adds with the same item number or something like that. I'm not 100% sure, but it's in the papers. So there, it was, again, that was more about the operation. That, yeah. So modular verification, I believe, is the key to efficient verification. And I think this idea of using interfaces to generate, this idea has been around. You do modular verification and you specify interfaces. And so interface grammars is a new way of looking at it. And there's a lot of work using finite state machines to kind of specify the interaction behavior. So this is a different way of looking at it. And I think there's a lot of things that can be done. One thing is we didn't, we generated these stubs, but we didn't look algorithmically like are there more efficient verification strategies now that I know I'm going to generate a stub which is going to be actually a parser? Are there classes of grammars where verification can be done more efficiently? So, there are all sorts of model checking issues that can be investigated. But so far what we have is an interface compiler, and it will generate you a Java code, from the given interface grammar. Okay.
I wonder what is your model of concurrency in that? I assume your model is a one-to-one relationship between a calling object and a server object. So if there are multiple objects calling a single server object, what happens?
Yeah, we didn't handle concurrency at all. So thanks for the question. So concurrency we didn't handle at all, and so we looked at it. It gets very tricky actually. So the most general thing we have now actually there's one object and then there's other object, and that's the interaction between those two. For WSDL with the web service stuff, so that's what we have. The structure works, but yeah, I mean concurrency is an issue. Yeah, it will be hard to handle. But I mean, you have to extend the language basically. But yeah.
So. Why the hell did you use these old-fashioned grammars? Why didn't you provide the user with an interface to build an automata and thereby do all this specification stuff, which would be, I think, easier to access for an average user?
Okay, so I don't, so this automata, use automata. So how do you, I mean, writing state machines, I argue that actually writing it as a grammar is easier. I mean, automata, what are you going to write? You are going to write transitions, right? I mean, it's nice for...
It could have a visual interface.
Exactly.
It could have an editor for that.
Exactly, right? So it looks good on visual tools. It looks good on papers, the automata. But, most people still develop software without visual aid. I mean, this would be... I think it's a different style. I think it has benefits. You don't need a visual aid. But you're right. I mean, so automata is another way of doing it. So technically, I could always say this is more expressive.
Perhaps this is the complement to the concurrent client question, but a bunch of servers are sort of products of little servers, or you might just say a dispatcher dispatching to a couple services. Right. And in that sense, you can interleave, transactions with all these other services. Is there a way of easily saying that a service is a product or a discriminated product of other services? That's the interleaving of them. And would that simplify some big, complex APIs?
We didn't look at composition of services and we looked at just WSDL. Now, one could think of, maybe you have like a BPOS specification which composes some other, services, and what would it mean to generate some, interface for that? So we didn't look at that, but with the interface grammars. But that would be something. And so if you have the general question would be, I have a bunch of interface grammars and showing different components. So now I want to check different components and how do they compose. So we didn't look at that. So we are really at the beginning of this where one client, one server. But yeah, that's definitely in addition to concurrency, there's another thing there. I mean, even if you just had a sequential program, how do you compose interfaces? Yeah.
So I have a question. Have you looked at JMock and EasyMock? So that they let you basically, they'll create like an abstract subclass or an anonymous subclass, and let you attach expectations to it. And it's kind of grammar-like in the way you can,
No, I didn't. We should.
Okay. Yeah, I don't know what's behind the implementation, but there might be some kind of parser in there.
Right. Yeah. Thanks.
Oh, go ahead.
I never quite understood. I mean, Java Pathfinder, that's an explicit state model checker. Right. And my intuition is always say horrible for modular verification. So let's say you have a function x plus 1. Right. Then for Java Pathfinder, it's much cheaper to execute the function and do x plus 1 than any abstraction of foo you're going to come up with. So it's going to be slower. So I can see like for EBJ, once you remove lots of lines of code and you have a narrow channel, then you introduce abstraction, it's still going to be okay. But if you have a non-trivial client and you want to keep modularity, create smaller and smaller modules, at some point the explicit state model checker is going to be completely useless, or your abstraction is going to be completely useless.
I think there are two answers to that. One easy answer. JPF does not handle native code. So you have to do this. So forget about modularization. If you do some network communication, you may not have access to the implementation of that other component. So you have to do something. That's the easy answer. Now, the more difficult answer is, yeah, there is this thing about non-determinism versus the size of each state that you have to store. Now, because if you add more components, maybe you are going to reduce the non-determinism, but now the state description is going to get bigger and bigger, right? Because I have to store all this other component that I removed. So where is the, that threshold between you reduce the state space so much that actually non-determinism is not hurting you now because you removed a lot of state information about that other component. So your state description is much smaller, although you may be visiting more states, right? So that actually, that's an issue for the examples we had, there was no other way of doing it. So, but the efficiency issue is a good issue to investigate. So where is this threshold? And so we didn't do this just for JPF. JPF was out there and it had this native code problem, so it was a natural match. But the way we think about it is basically we provide you an interface. There's some non-determinism in it. You hook that non-determinism to your model checker. I don't care what your model checker is. I don't know if it's symbolic, bounded, whatever. Now you can, check this simple system modularly. So.